What is Apache Iceberg and why is it displacing Apache Hive? If you work in data, there's a good chance that you've either worked with or still work with Hive tables. While older technologies replace newer ones every day in the big data space, this change promises to upend big data as we know it. Excited? Let's dive in. This is the top 5 reasons that Apache Iceberg is replacing Hive. Reason number 1, outdated architecture. The single biggest difference between Hive and Iceberg starts at the architectural level, and a lot of that has to do with one key difference: metadata. Hive and Iceberg both collect metadata about the datasets they store. The difference comes in both the scope and type of metadata collected. Iceberg collects more metadata than Hive, and also collects certain types of metadata that Hive doesn't even collect at all, relating to changes in the state of the dataset. Like the two other data lakehouse formats, Delta Lake and Hudi, this provides a layer of abstraction on top of the raw cloud object storage typically used in a data lake. Unlike other table formats, Iceberg is inherently open, containing a rich set of features. This essentially turns the same data lake technology underneath it into a technology capable of meeting and surpassing the analytic workloads of any data warehouse. In addition to this, Hive and Iceberg differ in the way that they track data. Hive tracks data at the folder level when working with data in a table. This can sometimes cause data to appear to be missing when file operations are performed on object stores like AWS S3 or Azure Blob Storage. In many ways, this is a sign of Hive's age. Although it's often used today to query object storage data lakes, it was designed for much older Hadoop clusters. These deficiencies are importantly baked into the Hive architecture and cannot be fixed. In contrast, Iceberg keeps track of data at the file level. This vastly improves the efficiency of operations on object storage. It means that expensive list operations are no longer needed in the way that they are in Hive. This makes Iceberg a particularly good fit for data teams working with large volumes of changeable data based on cloud object storage environments like S3. Increasingly, these storage technologies make up the bulk of cloud storage, making Iceberg a safe bet for the future. Reason number 2, performance. Hive is old, and part of that age shows up in poor performance. Some of this relates to the size of modern datasets, which now greatly exceed the original sizes imagined when Hive was built. Once again, the folder-based directory structure ensures that inefficient list operations are required, slowing performance considerably. This is particularly true when updating or deleting a dataset frequently. Hive was never designed for these operations to be routine. This causes high latency as Hive requires all updates to replace the entire folder each time. In contrast, Iceberg is built with change in mind. Its advanced metadata collection and management ensures that every change is tracked in a series of snapshot files, allowing for much faster updates and deletes. Snapshots also eliminate the costly and slow folder level updates, allowing the engine to read from the metadata in a much faster manner. Similarly, Iceberg is much faster for partitioning. To achieve this, it skips irrelevant partitions, deploying a more granular partition strategy than Hive. Once again, Iceberg's partition strategy is based on change and is baked into its architecture. Overall, Iceberg allows a more efficient data manipulation language across the board, particularly on the cloud object storage used widely, whether it be on AWS, Azure, or GCP. Reason number 3, cost. Hive's architectural deficiencies come with an interesting financial cost to organizations using it. Because schema changes, updates, and deletes are so costly in Hive, one common approach is to rewrite the entire dataset when a change occurs. This often requires a manual setup for partitioning data, which can be time-consuming and error-prone. Apart from being slow, this also increases storage costs, ensuring the worst of all situations, an inefficient and inexpensive operation both in terms of time and money. This problem is duplicated for retrieval. Each time you query data in Hive, the directory needs to perform a list item. This drives up compute costs and gets even more expensive when considering multiple partitions. Iceberg is designed to absorb change easily, and part of that approach yields cost savings. Iceberg supports in-place schema evolution, allowing you to evolve and change table schemas without requiring costly rewrites. Meanwhile, snapshot files eliminate costly and slow directory listings, allowing the entire engine to read from the metadata. This provides a much faster and less expensive alternative compared to reading the entire dataset. Reason number 4, easier data manipulation. Iceberg completely changes the way that datasets can be manipulated. This includes new abilities to allow data to be inserted, updated, deleted, and merged in ways that were difficult in Hive. In fact, Iceberg allows for ACID compliance when using cloud object storage, something not possible when using Hive. ACID is an acronym that stands for atomicity, consistency, isolation, and durability. If a system achieves ACID compliance, it is suitable for transactional data management. If it does not, it cannot be used readily for these kinds of operations. Hive is not ACID compliant and never was originally designed to take this level of consistency into account. Instead, it was designed only for analytic operations, never transactional ones. And although there are some new initiatives meant to push Hive further towards ACID compliance, these are afterthoughts and not built into the architecture from the ground up. Iceberg, in contrast, was designed to be ACID compliant from the very beginning, and an attention to data consistency and integrity was built into the system from the ground up. This means that it can handle workloads that require ACID compliance, including those used by transactional data systems. This is essentially the dream on which all data lakehouse technologies were born, and it makes data lakehouses running Iceberg suitable for applications that would never have been possible before. It allows datasets to adhere to use cases and compliance requirements such as GDPR and others. Reason number 5, ease of use. The last reason is also the most important. Hive is just not easy to use. Iceberg is very easy to use. Hive requires extensive rewrites, folder-level updates, and does not adapt to change well. Iceberg is designed for fast-moving modern data. Change is built into its architecture, and it's much easier to use because of this. That's our 5 reasons, but there's room for a bit more. This is the part of the story where Starburst comes in. Although there are many ways that you could deploy Iceberg in place of Hive, the very best way to implement a data lakehouse based on Iceberg is by using Starburst powered by Trino. At Starburst, we call this particular architecture Icehouse, and it amplifies the advantages of Iceberg itself. Both Starburst Galaxy and Starburst Enterprise run on the Trino query engine. Iceberg was literally built for Trino when it was first developed at Netflix. As such, Starburst is uniquely positioned to take advantage of Iceberg and to maximize its openness alongside Trino's own openness and scalability to build a powerful, truly open data icehouse. If you're interested in learning more about a data icehouse architecture, there's links in the description below. The shift from Hive to Apache Iceberg represents more than just a change of technology. It embodies a paradigm shift in the world of data management, signaling the rise of the data lakehouse era, and specifically the icehouse era. And this, more than anything, promises to remake data as we know it.